all gone very quiet. Is it that postprandial torpor that descends? Now here comes the science bit, because we're worth it. A post-lunch pick-me-up and a nod to the wonderful innovation that has taken place here throughout time at the Royal Institution. And we're here today, of course, to find a new model for economic growth, inclusive growth. This morning we heard about the fiscal environment that's needed to drive inclusive growth and what more can be done to make sure innovation itself is inclusive. As Charlotte Aldrich, CPP CEO, pointed out this morning, there seems to be a consensus about the conditions that are needed for growth, but a very different set of opinions about how you actually achieve it. How do we get there, especially under the conditions that we find ourselves right in at the moment? Much like growth then, the conditions are needed, the right conditions are needed to keep a fire alight in a tricky environment. You see where we're going with this, can't you? Not too laboured or anything. The Royal Institution science communicator, Jemma Naumann, is with us this afternoon to demonstrate exactly how this works. And then I will try to provide a sort of metaphorical interpretation. Bear with me. It's a long time since I did a chemistry lesson. Jemma, come, tell us what you've got. Tell us what you're going to be doing.
Thank you. I just want to start by saying it's so great to be here today to do some science for you. And I wanted to start off with this thing that I've got here, which I'm sure all of you recognise. It is a candle, and we've got the candle burning very bright. Now, this does have some history to this building that you're in today, the Royal Institution. It was a guy by the name of Michael Faraday in 1825 who started the Christmas lectures, a series of science lectures for teenagers that are still done to this day. And he did several of them on the chemical history of the candle. So fire does need some very specific conditions for it to burn. It needs fuel, it needs heat, and it needs oxygen. And if you remove one of those conditions, say for example, if we snuff the candle, then the flame goes out. Now, fire burns hot and it burns bright. And an extreme environment for that is going to be something that is the complete opposite temperature. Now, when I do these presentations for children and teenagers, I like to ask for hands up for some ideas. So anybody want to put their hands up for an idea of something that is quite cold that we could use that maybe might put out a fire? Anybody? Ice is very cold, thank you so much. Ice is very cold, so frozen water. I'm thinking even colder than that. Yes. Liquid nitrogen, yes, liquid nitrogen is what we can use.
Very good,
excellent. Thank you. So liquid nitrogen is minus 196 degrees Celsius. So it is extremely cold on the opposite side of the temperature scale when it comes to fire. So I have some liquid nitrogen in this dewar here. Now, it was a scientist by the name of James Dewar who also did work here at the Royal Institution who invented the dewar. We now know them as thermos flasks, so keep things hot and keep things cold, especially our warm drinks at this time of year. And if I pour a little bit of liquid nitrogen out, we can get a good look at it. So nitrogen is usually a gas in our atmosphere. We cool it down to minus 196 degrees Celsius, and we can turn it into a liquid. And you might also be able to hear that boiling away in there. So boiling, just turning from a liquid into a gas. Now, it's such an extreme environment, and I wanted to just show you how extreme it is. So I've got a few flowers here, and I'm going to place one of these flowers into our liquid nitrogen, just so we can have a look. So I'll place it in there. Again, we can hear that boiling away. I'll leave it in the top there. We can hear that boiling away. Now, flowers, a lot of organic material, they contain lots of water. So because the liquid nitrogen is so cold, it's going to freeze the water in those cells. And then if we then lift it up, It completely crushes, yeah. So we're freezing that water, we're completely destroying those cells, and it leads to a change in between those flowers. If I try and squeeze the flowers as is, they're not going to break apart just like that. Now let's bring that back to some fire, because that's, again, what we want to see. Will fire burn in this extreme environment of minus 196 degrees Celsius? Well, I'm not going to use my candle. I'm going to go something a little bit hotter and a little bit brighter. I'm going to use something called magnesium metal that I've got here. Now, some people might recognize this from an experiment done back at school. We burn magnesium metal. But magnesium was also first isolated in the Royal Institution in 1808 by Humphrey Davy. So again, more history to that one. What I'm going to do is I'm going to light this magnesium metal in the flame of the blowtorch, and then I'm going to bring it over to the liquid nitrogen, and we're going to see what happens. Now, first, a little bit of safety. It is extremely bright magnesium metal, so bright almost like it's like you're looking at the sun in a way. So if you don't look directly at it, just look to the side of the when it's burning through your peripheral vision, just to protect your eyes when we're doing this one. Okay, so I'm going to get this one ready to go. Also, when I do this with the kids, I like to do a bit of a countdown. So if you'd humour me, we can do a countdown from 3.
Yeah.
Yeah?
Yeah.
Okay, so counting down from 3,
3,
2, 1. And then burn, it's very bright, and then, okay. So it's gone out in the liquid nitrogen. So even though it's extremely hot and burning very, very bright, still going out in the liquid nitrogen, because we're losing some of that heat. So that heat, that oxygen and the fuel required to keep the flame burning. But I'm not going to end on that. I've got one final thing that I'm going to show you, because if we add another condition to that magnesium, then perhaps we can get it to burn. Now, I'm sure all of you probably recognize one of these. We're in a festival and celebration season at the moment, so lots of sparklers going around. Sparklers also contain magnesium metal, but they also contain something called an oxidizer. So when it burns, it's able to supply its own source of oxygen and burn very bright. So again, this time I'm going to light this one, and then we'll put this into the liquid nitrogen to see what happens. So one last time, one last countdown from 3, 2, 1. All right, we've got our sparkler going. And it continues to burn, even in the liquid nitrogen, at minus 196 degrees Celsius. So I'll leave that one in there to let that burn. But thank you so much for inviting me. Thank you.
Jemma, thank you very much. We all wish we'd concentrated much harder now, don't we? Because chemistry is really good fun. Jemma, Naumann, thank you very much for demonstrating this to us. While Jemma clears away, esteemed members of the audience, let's interpret what we've just seen through the prism of inclusive growth. It seems obvious, doesn't it, that a hotter fire is what's, yes, it's quite smoky. A hotter fire is what is needed in a very cold environment. But when that hypothesis is actually applied, in this case, the fire goes out because the conditions in that jar of liquid nitrogen were just too hostile. So it can be argued with growth and growth policy. While a hot and fast approach might seem the best remedy to a cold, stagnant economy, when put to the test, it could still fizzle out if the conditions aren't right. The coldness of the flask, for example, or the market is easily observed when oxygen is missing. The right conditions are not there. And so our friends at the Centre for Progressive Policy might consider an understanding of the need for growth to be inclusive of people and places is the oxygen that we need to keep good growth alive. The sparkler that combines the fuel and the key ingredient of the oxidizer represents the growth stimulus and this inclusive approach that we're talking about today. It can withstand the difficult environment of the flask or the market and still burn brighter than before. I hope that that has given you a little food for thought, and you'll bear it in mind throughout the afternoon. Once again, to Jemma, thank you very much.